Hello. Let's answer this problem from the 10th Philippine Mathematical Olympiad, which is part of the IMO qualifiers program in the Philippines. For this problem, we are given an equilateral triangle ABC. We let the ray AB be extended to a point D such that B is the midpoint of AD. A variable point E is taken on the same plane such that DE is equal to AB. If the distance between C and E is as large as possible, what is the measure of the angle BED? As with most geometry problems, let's start with illustrating the problem statement. We first draw the equilateral triangle ABC, and as an equilateral triangle, the sides of ABC are congruent. Note that for this illustration, we'll put tick marks for congruent segments as shown here. We extend AB to get a point D so that B is the midpoint of AD. Hence, we can conclude that BD is actually congruent to the sides of triangle ABC. So we put another tick mark for segment BD. Now we choose a point E, let's say this golden point, so that DE is equal to AB. In other words, DE is congruent as well to the other segments we have identified so far. What we want is point E to be as far as possible from point C, which begs the question, where exactly should we place point E? What we know so far is that E is at a fixed distance from D, which means that the locus of possible points of point E is the circle centered at point D, with radius equal to that fixed distance. Hence, any point in this orange circle could possibly be point E. If we move point E around this circle, we'll notice that the farthest distance between C and E happens when E lies on the line connecting points C and D. Thus, this is where we'll put point E. Again, point E must be on this extension of line CD. Once we have established the position for point E, what we're left with is some angle chasing problem to figure out the measure of angle BED. We start with what is known, and that's the measure of the angles of the equilateral triangle ABC. Remember that for any equilateral triangle, each interior angle measures 60 degrees. So all the green angles here measure 60 degrees. For good order, let's track all the known angles in the blue table shown. When you are doing some angle chasing problems involving many other angles, I suggest that you do something similar so you don't mess up with the angles you have obtained so far. After getting these green angles, we can look at angle CBD, which is denoted here by the red angle. We can use the linear pair theorem in this case since points A, B, and D lie on the same line. Note that angles ABC and CBD are linear pairs, so they should add up to 180 degrees. So in other words, we can say that those two angles are supplementary. Eventually, we'll conclude that the measure of angle CBD is 120 degrees. Next, we look at the blue angles, BCD and BDC. Note that these are base angles of an isosceles triangle because BC is congruent to BD. By the base angle theorem, the blue angles have to be congruent. Next, we make use of the triangle angle sum theorem to conclude that the sum of the measures of the interior angles of triangle CBD is 180 degrees. If we let x be the measure of the blue angles and make use of the known measures of angle CBD, we get the linear equation x plus 120 plus x equals 180, which should easily be solvable with some algebraic properties. We conclude that x is 30 degrees, and so the measure of the blue angles is 30 degrees. Next, we make use of the linear pair theorem, again, to conclude that the measure of angle BDE is 150 degrees. Lastly, we look at the golden angles DBE and BED. Note that BDE is another isosceles triangle like CBD, so we can use the same theorems and arguments we used earlier to get this measure of the golden angles. We let y be the measure of angles DBE and BED, and then we'll get the equation y plus 150 plus y equals 180, and eventually conclude that y equals 15. Therefore, the measure of angle BED is 15 degrees. And that's our final answer. I hope you learned something from me today. Thank you for watching and see you on the next one. Bye-bye.